It's a great pleasure for us to introduce our third speaker for today, who is going to talk about his work as a researcher at Istituto Italiano di Tecnologie, the Dr. Victor Barasoul. So I now delighted to hand over to Dr. Victor Barasoul, who can tell us more about the exciting work that he is doing and about his topics, that is quadruped robots from the design to the use of artificial intelligence at IIT. So over to you, Dr. Victor Barasoul. And again, nice to meet you. Let's start.
Okay, nice to meet you, Jose. Thanks for the invitation. Yeah, I'm enjoying a lot this opportunity to talk a little bit more about quadruped robots that nowadays is more and more present in our lives. I'm gonna try now share the screen. Let's see if everything goes smooth. Let's see. Okay, do you see my screen?
Yeah, we can see your screen.
I'm gonna shut down my camera just to save bandwidth for the transmission, because I have some videos and I don't want to get them like stopped. So
perfect.
Okay, do you see my screen?
Yeah, we can see your screen. Everything is fine. I can see. Okay. We can see.
Okay, good. If there's any problem, or if the call is shutting off or cutting off, you let me know. Then I can come back. So I prepared this presentation, and it's like a mini workshop in quadruped robots. This it involves many aspects of quadruped locomotion. I'm talking about the design, mechanical design. I'm going through the sensors. I'm going through some concepts till the implementation of some, but always high level, of some techniques using artificial intelligence. So if you pay attention to what legs can do, you see they are quite robust when compared to vehicles that use wheel. You can see that you can go over very rough terrain. You can adapt to rough terrain in a high speed when you like the mini cheetah is showing. You can navigate through very discrete and challenging contact points. You can use them, and on the very bottom on the right, you can see that the legs can even act as an active suspension. So it's blocking a little bit nowadays. So okay, here. So nowadays we already find some quadrupeds in the market, starting with Boston Dynamics, that is the most modern, let's say, machine, but it's not ideal for research. There is Robotics that now launched the Animal C. It's a platform that is quite robust, good for navigation and good for research. There's also military application and also other cheaper robots trying to enter the market for that also can be used for research, like the robotics, the unitary robots. So I'm going to talk a little bit of IIT. Just to introduce, IIT is, as you see the name, is an Italian Institute of Technology. It's spread all over Italy, with 11 centers and 2 outstations in the US. We have the biggest center in Italy. We are now growing. We're about 1,500 people at IIT in Genoa, with 3 buildings, and we are the one of the poles that works with robotics. We have more than 60 countries. I mean, people from 60 countries on all the 5 continents. And I'm personally working in the lab that is called Dynamic Legged Systems, that is led by Claudio Semini, with more than 14 years of experience. We start with a leg, then HiQ. I think around 2013, 14, Job was in the lab also doing. We now have the last robot that is HiQ Real. I'm going to talk a little bit about. So the outline of this presentation goes through the mechanical design, understanding the importance of the force torque control in the robots, some concepts in locomotion instability, mathematical modeling in challenges. We're gonna see a little bit of the components behind a control framework for a quadruped robot, and also an application of artificial intelligence for them. So let's start with the mechanical design and the main components. Well, we start with the chassis of the robot. Was this one of part of the main components. We have position sensors in the joints. We need to know where the link is positioned. We have the actuators that might be electric, but now I'm focusing on the hydraulic. That is our expertise. That can be rotary or linear cylinders. We have torque sensors or force sensors like load cells. We have perception sensors like the inertia measurement units that works like our labyrinth to understand our orientation in space. And we have also cameras that collect exteroceptive data, let's say, to fuse and build some perception. And the computer, that is the brain. So as a mechanical design example, I'm going to show the development of high Q to max when we migrated, when we evolved from high Q high Q on the left, that is high Q stands for hydraulic quadruped, and we wanted to design a robot that was more rugged and powerful. Then we designed for high Q to max, and I'm going to talk a little bit about how we designed that. So the design is quite complex and interactive because you need to start from the definition of the mechanical efforts that the robot needs to know, the robot experience when doing the task and performing the task. So first you need to define the task. Then from the task you can extract mechanical efforts, and then you need to look at the market or to the actuators that you have in the market, or if you need to also customize them. If you find something for the that can deliver that mechanical efforts, and then you might get all the specifications in terms of mass, inertias, and everything, and you put back into the initial system, and then go again and see if you're still inside the envelope. So how do you know the task the robot needs to do? What we do is to collect what we call characteristic motions. For example, this is the basic crawl gait. We have crawl gait on stairs. So we run the simulations and you understand how much torque, how much speed we need. We have a trot that is used for fast locomotion. You have also to trot and to turn, so that we are understanding how we use also all the actuators on the robot, all the degrees of freedom for the motion. We have rough terrain when you have impacts, so we put the robot to work on regular shapes. We see what are the torques, forces that the robot experiences. We need to be able to recover from external disturbances. So here we are applying external disturbances. You don't see that, but there's a force pushing, the robot needs to recover. So there will be peaks and the forces that we need to also couple with that. And in this specific design, we want the robot to self-right. So in case of a fall, we wanted the robot to be able to recover from that, and stand up again. Once we run all the simulations and we put them together and we concentrate that, we can understand how much torque every motor needs at a specific position. So we are mixing plotting all the torques together, and then we get this chart. If we then move all that efforts in the, let's say, in the convention of the actuator, because we're going to use the same actuator for all the joints. We want to do that because we minimize the cost and the design. So with this projection, we see how much one actuator needs to do. So here I'm showing 3 joints. I'm showing the hip abduction, that is the one that open and close the legs laterally, the hip flexion extension, the ones that move forward and backward, and the knee. The knee is like our knee, so it goes maybe up and down. And according to these plots, we need to select the actuator. Here, I'm going to give an example of the knee, because knee is a critical joint that has a lot of effort. And the knee, for example, it's in irregular shape. And then what we need to do, we need to find a way in the mechanical design when we're designing the transmission for the hydraulic system, because we have a piston. So from a linear actuator, we need to produce a rotary motion, and for that we need a mechanism in between. And this mechanism, they might change. They can be a hinge link on the top right, can be a 4-bar linkage, and can be an isogram that works like our knee. Our knee has this mechanism like an isogram. And if you look to what they can deliver according to the range of motion, they have different shapes. And you wanna trade off between the complexity of the mechanism and the torques that the mechanism can deliver. So in our case, we chose the black curve, that is the 4-bar linkage. Another important aspect is the workspace of the robot. So for HiQ to Max, we needed the robot to self-right, and wanted more range of motion, because the range of motion is important when you have reflexes that the leg needs to retract fast, or when you go over stairs, because the robot will tilt, will incline to be parallel to the inclination of the stairs. And in that situation, you need a lot of workspace to move the leg, to swing the leg, as we say, from one contact location to another contact. Of course, after mounting, we also do let's say endurance tests. So on the left, you see trajectory tracking at a 5 hertz sine wave. Hydraulic is super powerful. I mean, it's really powerful. It can deliver torque, force, and speed at the same time. What is something that is hard to achieve with electric motors, mainly when you're working with bigger robots. No, in this video on the right, the robot is jumping. It seems to be jumping easily, but the robot is carrying 25 kilograms. So we even broke one leg doing this. After that we improved the mechanism. This is when we released by that time the robot, the first demos we did in Rome, in a conference, where the robot is just trotting to show omnidirectional locomotion and the self-righting motion that we designed. That was part of the requirements for this design. So after HiQ to Max, we decided to move on. And one of the problems with HiQ to Max was the reliability of the components. We were having many problems with some components, and we want to have a more robust robot. And more than that, we want the robot to be autonomous. So we didn't want to have a hydraulic power unit outside the robot. No, we didn't want to have an external pump to pump the oil into the robot, and then because otherwise we will be constrained to the lab always. So in 2016, we teamed up with Moog, that is a multinational company that leads the section, the sector of special components and motion components for motion generation. And we teamed up with them to design this robot and also design the components for this robot. So HiQ Rio was a project where we wanted to design this autonomous leg platform. And one of the first things that we did was to create these smart actuators. So on the left, you see common components in a hydraulic quadruped. So you have the cylinder, you have the amplifiers for the valve, you have encoders, you have load cell to measure the force of the cylinder. And what we did with Moog was to develop this smart actuators that is a cylinder that has everything inside, that is 3D printed in titanium, and also these smart manifolds that are also 3D printed in titanium. So this smart actuator has all the electronics on board. It has pressure sensors inside. It has relief valves that protect the component in case of a high pressure in the chambers, that it opens to tank and release the pressure. So it has the load cell, everything is inside, and has the encoder also magnetically printed on the, let's say, on the piston with a micro precision. In our lab, we test all these components to be in a situation closer to what the robot experiences. So on the left, you see a rotary unit where we have a flying wheel that has the same inertia of the leg. So here we try trajectories, we block the system to see what is the response of the system in blocked condition, and try to reproduce situations where that the robot will be facing, so the actuator will be facing. And the same for the leg. So yeah, I'm gonna then now go to the second point. And this is about joint torque and force control. I don't know how much of you had experience with a robot manipulator arm, or even controlling a motor. So there are two ways you can control a motor or an arm. You can control in position. That is mainly what is used in this automotive manufacturers, the mounting cars, but it's super stiff and dangerous, mainly if you're in contact with humans or environment that you cannot damage, when the robot is traversing it. And for that, to cope that, we have torque control. So the robots can also be operated in torque control. And torque control means that you have a control on the actuator where you want to deliver a certain amount of torque. And when you achieve this capability, when you have this capability on your actuation, you can do many things. And this is super powerful. You can control the force, and then you can interact with the environment. You can, in the model, you can do things like this. You can compensate the gravity, and then the leg just behaves as it was in a space with zero gravity. We can impose an impedance, and we can modulate this impedance. So now, what is impedance? Impedance is what for mechanical systems, the impedance is the mass, is the inertia, is the damping, and is the spring characteristics of this of the system. So in a legged system, we want to be able to dictate how the leg will behave in case of a contact with the ground, an expected contact with the ground. And if you have torque control, you can adjust this spring and this mass system. And this gives you some prediction in case of an unexpected contact with the ground. So here we have an example of our torque control loop. So for who already had experience with control and control theory, this is the response of our actuator in blocked conditions. So it's almost 100 Hertz bandwidth in case of a step input. And this is the final product when we mounted all the actuators and yeah, start testing the high level commands. So we have the level that is the torque control at the actuators, and we have the high level that is the motion generation and control of the robot, so that generates the stepping and stabilize the trunk. So in 2019, we had the inauguration of this robot, and to show what we could do with this robot, we pulled an airplane in Genova's airport. This is an airplane of 3.3 tons. And of course, the robot was not made to pull airplanes, but that was showing how powerful the robot is, and that could pull hydraulics. And we have also some making of this trial where we were in the lab understanding how much the robot could pull. And we developed a code especially for that, where the robot is taking a step only if needed. So I'm in the back with the joystick, setting the amount of force that the robot needs to pull. And then I call for that pull, and the robot then pulls, and in case the load moves, it takes a step to keep the stability. We also did some tests in the back of the building with my car, where we were pulling my car, and that was super easy without pulling the brakes. So pulling the handbrake with 5 clicks, it started getting challenging to the robot, but the robot was still able to pull the car with 5 clicks. And this is a 600 newtons. Okay, let's move to locomotion and stability concepts. Well, legged systems, the dynamics and what happens during the locomotion can be characterized somehow with these three parameters: the step frequency, that is, it's a kind of obvious; the duty factor, that is the ratio between the lag the lag in support phase and the lag in the whole period of the step, and the step length, that is the distance that the body travels during the support. I mean, biologists, they had studied nature for a long time, and they already documented that there's a relationship between the gait, the body speed, the body size, and the mass with these three parameters. And this serves as a kind of inspiration for us when we design the controllers. Now, talking a little bit about the stability. Here we have this cute cow, and let's consider that, you know, this leg is standing up with 4 legs on the ground, and every blue point of this blue circle is a contact position, is a support, contact support. And if we draw lines in between them, we can create this support polygon that is the basis for the idea of stability. Now, if we project the center of mass of this coal that we are speculating that is in there, that position, and project inside this polygon, if this projection always reside inside this polygon, we consider that the locomotion is statically stable. Now, this kind of locomotion you can see in a crawl gait. So in the crawl gait, you have always one leg lifting at a time. And to be statically stable, the projection of the center of mass must be always inside this support polygon, no, created by the support legs. Now, if we use instead a trotting gait that is used for higher speeds, we're going to notice that there's no way to have a polygon because you have only diagonal lines supporting the robot. No, so there's no way. That's why the trotting gait is a different gait that is called the dynamically stable gait, because it's only stable if the robot is in motion. If the robot stops, the robot falls. So we call dynamically stable gait. Okay, let's move a little bit to the math, but this is going to be really brief. I'm going to start super simple because, you know, everybody knows this equation, force equal, so as a force and a mass and acceleration. We can just invert the equation. You know, this is basically saying that there will be acceleration for a given force applied to a certain mass. And let's just change a little bit the variables here. Let's call A like Q double dot. And if you think about the J that we call the Jacobian, this is basically for a one-dimension system. This is the lever arm. So if it's a rotor actuator, this J is a lever arm. So what it's saying is that, yes, there's be a force that somehow produces a torque inside on a mass that accelerates with a quantity of Q double dot. Now, a quadruped robot has a more complex behavior because this is not only one body, but a quadruped robot is a multi-body system, and more specifically is a floating base system because the base is not actuated. If you think about the robot has 18 degrees of freedom, 18, no, 12 from the joints that we are trying to actuate. We have one actuator per joint, and we have 6 degrees of freedom. That is the roll, pitch, and yaw, and the translation of the base that is not actuated. That's why we call floating base. So the torso is a floating base, and in this big equation, where you have in the first term inertia effects, then Coriolis effects, the F is the friction, G is the gravity effects on every link, that is going to be equal to the torques that you send and the external forces on this on the limbs. This equation we call the forward dynamics and inverse dynamics according to what you want to do. If you, with this equation, you can understand what's going to be the evolution of the system, but also if you know the motion that you want, if you know the motion you want, then you can plug this motion into this equation, and you can know the torques you need to produce that motion. So it's a very important equation. And why this is very challenging and complex. So in a legged system, can be a biped, an hexapod, or a quadruped, we cannot act directly on the base. So we need to control the base through the ground reaction forces generated by the legs on the ground. But these ground reaction forces, they will be created due to the joint torques, no, due to the torque at every joint. So that is the tricky, is through the joint torques that we need to generate the ground reaction forces, and that is a huge nonlinear mapping between them. It's a nonlinear system because of all these matrices. They are nonlinear. It's underactuated because we have a floating base system. So we have 12. Sometimes we have 12 actuators for 18 degrees of freedom, and it's also a system that has hybrid dynamics. What is that? It means that according to the legs in contact, you have a different dynamics. So according to the legs in touch, you have a different equation that represents the evolution of the system. So now going to the last part of the talk, I'm going to talk about the main approach for motion control and generation. So we mentioned about the ground reaction forces, and this is one of the basic skills to stabilize and control the robot. So when the robot is walking and locomoting, it's really important, as this dog climbing, to be able to project properly the ground reaction forces. So in this video, we see these arrows. These arrows are representing the ground reaction forces that we need to project, and these red traced lines, they are the friction cone. So if you think about friction, that this is the coefficient, according to the friction coefficient and inclination of the surface, you have this friction cone. And if the force goes beyond this line or out of this cone, then the robot slips. So it's very important that having the knowledge of the friction and the surface to properly project the ground reaction forces, otherwise the robot slips. So this is an important skill. Another important skill is to be able to equilibrate the robot, is able to control the center of mass of this robot. So here I'm showing a video with a very challenging situation when you have two legs on the ground, trying to more or less simulate what the little goat is doing with the monkey on the back. And this is really particular situations, challenging particular situations when you have specific contact locations you can go over. And for that, you need specific techniques. In this case, it's a momentum-based technique. And another important thing, like the cat is doing, you need to know how to precisely place the leg. For example, here we were showing an experiment. The robot needs to cross without stepping inside the gaps. So as the cat, when you have irregular surfaces, you have only specific points you can step on, and the robot must be able to recognize where is the best place to step. That is fundamental. So what are the main components that try to carry all this idea? In a control framework, you can find, let's say, three main components. The perception is one of the most important, because without perception, the robot doesn't know where to go. No, doesn't know where it is, doesn't know how it's oriented in the world. So perception is very important. And what we do in quadruped system is to fuse many sensors, because every of one of these sensors, they can estimate something and don't estimate others. But since we need everything, let's say, to be simple, we need to fuse them. So the IMU gives us the orientation, rho and pitch of the robot, how the robot is oriented in the world, and also what are the accelerations, but doesn't give us velocities. So the velocities are actually extracted from the legs. But all of this has inaccuracies, and the robot will drift in the space. For that, we use cameras and lasers so that we can understand how much we moved according to a certain object or surface once we recognize these surfaces. And we can correct for that. So we do sensor fusion for perception. Then we need to have some algorithm that will generate the motion of the legs and the motion of the body, understand what is the motion the whole multi-body system needs to do to get to a certain location. And also we need to have some algorithm that will stabilize that in case something goes wrong. So that we call motion control. On top of that, we have high-level commands that is deciding, now pick this up, now go to this location, now turn, now go down to go over the table, or something like this. Here I'm showing examples of these components. For example, the motion generation, that here we're doing a flying trot. We have a trunk controller that stabilizes the robot in case of a disturbance. We have push recover algorithms in case of a strong disturbance to come from outside, where the robot needs to know where to step to stabilize. And we have components that allow us to control the torso and set impedances for the torso. So we set the way the robot behaves in case of an interaction. We can have also perception at level of contact. So here we are estimating the contacts, and this idea of perception, setting the understanding where the robot is stepping, can inform, can update the motion control to distribute the ground reaction forces. Because the robot is expecting to touch the surface with the foot, but that doesn't happen. So he's applying all the ground reaction forces. So he's generating torques at the legs, at the joint, sorry, so that you get a specific force at the foot. But the foot is not in contact, actually, is the shin that is in contact with the ground. So if you have an algorithm that can detect that, you can then tell the system that the foot is not the contact point. What is the contact point is the shin, and that is, to be more precise, we will update the Jacobian that you use to produce the ground reaction forces. And in the same way, instead of trying to control the motion through the ground reaction forces, if the robot is sleeping and there's no way to generate that, you can instead generate a motion to overcome the obstacle. So this is a feedback, understanding a collision, an anomalous collision, that you can also feed back into the motion generation. Now, to generate the motion, what do we use? We can use this complex equation that now it's going to be really hard, and I think it's hard to you to understand, even if for many of you it's the first time having the contact with this kind of topic. But normally, to use this full equation, very complex, it's normally used in optimizers, and optimizers that try to find a complete motion that you in the end be played back, because it's really hard to compute really fast and have solutions really fast. So to be able to generate the references really fast, what we do is simplify the motions, use simplified models to have the motion. And these simplified models, they start from the inverted pendulum, because the inverted pendulum is the dynamics of an inverted pendulum captures the main dynamics of a quadruped robot in a certain for certain gaits. So now it's a bit hard to explain you the details about the various models, but you can start from models that consider the inverted pendulum, can be an inverted pendulum with some flexibility, some actuation, and nowadays what is mostly used is what is called centroidal model. The centroidal model gets the pose of the robot, understand what is the equivalent inertia around the center of mass for that specific pose of the robot, and consider all the inputs. So it reduces the system to a point mass with some inertia, and the external forces that are being applied on this point mass, and the torques that are applied on this point mass. So the last part of the talk, that is about the use of artificial intelligence. Let's understand a bit how this is mainly used in legged locomotion. So what I have seen so far is that machine learning can be used for four things in general. We can learn the high-level commands. So, for example, you can say this is the step frequency, this is the duty factor, this is the step length, this is the speed you need to go. And you have already another algorithm that you generate the motion for that. So what you're doing is basically just understanding what are the best parameters at the high level that modulates this low level that generates the motion of the legs. It can be used for environment classification to understand whether it is grass or is mud, or if there is water or there is a door that the robot can go. You can use machine learning for that. So machine learning is artificial intelligence, and then you can replace a simplified model by a neural network trying to capture non-linearities that the simplified model cannot capture. And you can also replace complex models that is really time consuming to be computed by a reduced model using machine learning. And this last usage is what we're gonna be bringing here in this presentation. For those that doesn't know what is the basic components of a neural network, I'm bringing here quickly, giving here an idea about what is in the end is a neuron for machine learning. You know, a neuron in the end, what is the beauty of the neuron is that it has many inputs and fewer outputs. So what the neuron is doing is processing something, getting information from many places, but outputting just few signals. So it does some processing of the information that is coming from other sources. So what we try to do, I mean, what machine learning try to do to imitate that is basically a mathematical operation where you get the various input signals that's coming x1, x2, x3 that can be the pixel of the camera, or can be the speed of the actuator, whatever it is, the problem you want to solve. And you're going to multiply by a weight, you're going to sum them, and you're going to perform an operation on that. And that operation will give a value in the end. So what machine learning is doing is let's say creating a big neural network formed by these single neurons, where they are interconnected. And the tricky, so when we say learn, from the mathematical point of view, what is being learned is the weights. This W1, W2, W3. We need to understand what are these weights, so that for a given input, we achieve what we want as an output. And then most of you have maybe heard about deep neural networks, and deep neural networks are actually neural networks that you have many layers in between the input and output, what they call hidden layers. So when you use deep neural networks like this, you can be used for example, these kind of tasks where the robot is learning how to self-write. So you let the robot there, you have simulations, and then you're gonna there be finding the weights of that neural network that can find the policies for this kind of motions. But what we did in our lab was to use a convolutional neural networks. This kind of neural network works better for images. And the problem we want to solve is this one. The problem that we wanted to solve is we want the robot to process the surface and understand where is the best place to put the feet. So the pipeline for this task is here described, and it starts with the prediction of the foothold. So first we need to understand, given the motion of the robot, where we expect the landing position to be, where the leg is supposed to step. So here we have this red ball. I don't know if you see my mouse, but there's a red ball, and this red ball is the nominal position is supposed to step. Around this red ball, in the top center, this red ball, we collect the map around it, and we run some heuristics that take into account the leg collision, the swing collision, the workspace of the robot, everything that is possible. And then from that, we say, this is the best location. So this knowledge of, for a given map, this is the best location, is passed to the neural network. And then this neural network is trained. This neural network on the bottom right is trained to understand that for every certain image, you have an optimal foothold. And this is what we do. And what we did that because computing all the heuristics that you need to decide about step is really expensive, and you cannot compute that quickly. So with the neural network, we can simplify that. So we do like a model reduction, and we can run many heuristics condensed, like dancing in a neural network. And here you see what is the gain that you can have processing those inputs. So you can have up to 200 times faster the computation of the map and the computation of decision for that. And this is the video you saw. And here the robot is traversing, the robot is reading the map, the maps are collected, and the robot is deciding where to step, given that. So he understands that if he steps inside the gap, there will be shin collisions, and that is not good because the robot might get stuck in that. This is another example to show that it doesn't depend only on the motion that we want, because in this task, we ask the robot to stay there, but I'm pulling the robot. I'm pulling strongly the robot and pulling the robot to enter the steps. And even if he's doing a motion that he doesn't want, since we are based on the prediction of the nominal foothold, the robot can adjust the steps. And this kind of technique can also be successfully coupled with techniques called model predictive control, where we can foresee the future states of the robot and get the future locations and process the future location with this neural network, so that the MPC, when computing the control action in the future, already knows what is the best foothold. So this is a recent work that we did where we are fusing MPC techniques. For those that knows MPC techniques, we need to know where are the contact points in the future. And with this technique, since the neural network is quite fast, we are able to also process the future steps and the future maps, let's say around the normal foothold, and then give to the MPC the footholds that are likely to be in the future. Yeah, that was my talk. Time open for questions. I'm very happy if we have many questions. I think we are quite in time and have a lot of time to discuss.
Great. Thank you very much, Dr. Victor Barasoul. Well, first of all, let me ask the question from the chat, and then we can move forward and listen to our audience if there is any other questions. We have here in the chat the following question that says, how could you consider the friction that exists in the mechanism? Or you can calculate I think the friction factor between in your mechanism.
So how do we consider the friction in our mechanisms?
Yeah.
This is the question.
Yeah.
Well, to be sincere, we do not consider the friction in our mechanism because, well, let's say there are two different, there are various kind of frictions, that you might find in your mechanism. For example, in a motor, in an electric motor, you basically don't have friction. You have very small friction in the rotor itself because you have a bearing, and that is really low friction, even though you could compensate for that. But then if you couple a gear ratio, a gearbox after that, then you also have the friction of the gearbox. Now, the fact of considering friction or not depends on also when you are closing the loop for your control. If you are reading if you're reading the torque after the friction, then you are considering the friction inside your control loop. And if you have integral actions or things like this, you can try to compensate the friction in your control action at the low level. So we do not compensate the friction in the high level. We are generating the motion because we assume from the high level that we can achieve that torque in the low level. So we are splitting the system. We have the low level system that is in charge of giving to the high level the torque that it needs. So this friction can be compensated or inside the torque loop, let's say, or through the high level task. But we don't do it from the high level task. What we do is we have the torque sensor at the very end of the transmission. So we are getting the net force that is going to the link. And when you do the force control, we are doing the force control, closing the loop at that point. So the friction is in between, and then the control loop compensates for that. If you instead for example, if you instead try to do force or torque control, what many people do through current control. So what I mean is that in the motor, is an electric motor, you have the constant that relates torque with current. So some of the people, they control the current, saying, okay, if I have this current, I have this torque. No, but if you have friction after that, actually you don't have that torque. Then you have problems. In our robots, by the time we are still closing, we are closing the loop, the torque loop after the friction. So we don't need to compensate for that because that is tackled by the control loop itself.
At the low level controller in your system, do you have only one controller or do you have a multiple control loops at low level?
Oh, that is a very interesting question. Very interesting question. I don't know if the person that asked it has the same thing in mind, but here we are talking about a hydraulic system. Yeah. And we need to do force control and torque control on a hydraulic system. So in a hydraulic system, you have the valve, you have so we have the dynamics of the valve, you have the dynamics of the fluid, so the pressure dynamics, and you have the dynamics of the cylinder, that is the mass that moves. No? So you could go through a non-linear approach, doing feedback linearization, and understand, model the whole systems, all the subsystems, and try to compensate with feedback linearization or backstepping, many techniques to try to then do the control. This is a non-linear control approach. This is one technique, right? This is one technique. We are not doing that yet, but we want to do that. We have feedback linearization in our robot HiQ. We do feedback linearization, so we compensate for the dynamics of the pressure, dynamics of the valve. And in the HiQ Rio, this one, since you are using industrial components, we are now starting with PID controllers. So the control loop that are running, the control loops that are running for this robot that you are seeing, it's actually a cascaded loop, of PID controls. It's a nested, let's say, configuration. So what we have a PID controller for the current. We have a PID controller for the torque, depending on the valve, because we have two kinds of actuators. In one of them, we can even read the spool position. No, the spool position is the part inside the valve that opens and directs the flow. The flow. So we have in the most complex system, that is the cylinder. We have a PID controller for the current. We have a PID controller for the spool position, and we have a PID controller for the force in the cylinder. So this is the PID loop. And then the high level is saying, I want this force. And then these three PID loops, they try to achieve that.
Understand. And wouldn't you consider to have a loop on acceleration?
No, it's a loop in acceleration. I don't see why I would have a loop in acceleration, because that is not a state we want to control.
Mm-hmm.
What we do is something called velocity compensation.
Mm-hmm.
That is an extra term, that is a feed-forward action that reads the speed of the cylinder and compensate that in the valve command, so that it compensates the pressure drop. We know that if the cylinder moves, the volume of the chamber changes, and naturally augmenting the volume, increasing the volume of the chamber, the pressure will drop. So since we know how much this volume is reduced given the speed of the actuator, because we know the area, we can then have a feed-forward action to compensate that pressure drop immediately. And that helps a lot uh, uh, tracking the torque or the force when the system is in motion.
Okay, understood. Very clear. Here, well, one more question from the chat. Let me read it. What happens if a sensor of the robot is failing? Is there some sort of alarms or of something that alerts of these situations?
Yeah, I mean, we have different sensors. No, we have proprioceptive sensors and we have exteroceptive sensors. The proprioceptive sensors are the encoders, the load cells, the pressures, these ones. And in this robot, if a pressure sensor fails or an encoder fails, we disable the system. So we turn off the whole system. So we have this. But this doesn't happen for all the sensors yet. For example, if the robot needs the laser to navigate, and the laser somehow goes off, the robot keeps going on. We don't stop the robot, but that might affect the perception of the robot. The robot might start drifting. The robot start maybe like a drunk person that drank a lot and cannot walk, is always walking and going to the side, going to the side, cannot stabilize. This is what happens when you have problems in the state estimator. The same happens with the robot.
Excellent. We saw a high-level controller. At first, I suppose that you implemented a linear high-level controller, or which one?
I didn't get this. I didn't get this question. Could you repeat?
What kind of high-level controller did you implement? Because we saw MDP, model predictive controller at the end, right? And then after that, before that, we saw, I think, another type of high-level controller.
Yeah. Now, I mean, it's really challenging to go into that in a talk short like this. It's as I said, it's a mini workshop just to give you an idea of components, and then you might get interested, and then you go outside on the internet, and then you go and look for that. But at least you have directions, you see how components and things that are involved in the control of like a machine. When I say high level, I say the algorithms that are generating the motion of the legs, and the algorithms that are generating the torques in the legs to stabilize the robot in case the robot is not going the direction we want. There are many ways of doing that. You can use approaches based on nature, as I did in the past, using central pattern generators. I don't want to be here speaking vaguely, so I don't want to be vague to you, but what I want to say is that you have many techniques you can use. The MPC is one technique that is really promising in legged locomotion. And what the MPC is doing is that we give a position in space. The robot needs to track that position, and what it's doing is generating the torques at the joints when the robot is in contact with the ground, so that it can produce the ground reaction force that you move the robot in that direction. But the MPC is not generating the commands to swing the leg. This is another part of the controller that does that. It's a controller that may use the CPG approach, as I said, or it can be a simple ASP line. You define a point in the future where you need to go, and there's an ASP line that does the swing of the leg. Send that commands. We have the position, have the velocity, have the accelerations. You can compensate for the accelerations. You can compensate for the gravity when the leg is swinging to achieve that location. Once the leg touches the ground, you have the controllers that stabilize the system, and the MPC is one of the controllers. So it's really hard to go deeply into this discussion and describe. The only thing that I can tell you, even in a high-level speech as well, is that MPC is really promising in leg locomotion, because the MPC can understand what the robot can do in the future, and he can dose, he can adjust the amount of forces along the support phase.
Awesome, thank you very much. Here you have a lot of questions for the chats. Let me read one of them. It says, you mentioned a controller computer as one of the main components. Are there special computing requirements such as GPU capability, GPU power consumptions, among others?
Yes, there is. Mainly if you are using neural networks. So neural networks, they are very efficient when you start using GPUs instead of CPUs, because of the construction of the GPUs. So if you have the heavy neural networks, for example, it starts getting challenging for a CPU-based computer to do that. It depends on the size of their neural network to do the inferences. Now, yes, you have. In our case, we have one computer. We have two computers actually in the robot. We don't have just one, because just one is not enough. We have one computer that runs the algorithms to generate the locomotion, that runs the MPC, that runs the algorithm that do the motion generation, that detects the ground reaction forces, and the algorithm that does the state estimation. And then we have another computer that only does mapping. So it's getting the information from the cameras, and it's putting everything together and generating a point cloud, and that is then responsible, this computer is responsible by sending the map to the computer that does the control part. So in a modern robot, or you're going to have one really powerful computer, or you're going to have two computers, one for image processing and one for control.
Excellent, thank you. The other question is about the challenges on pneumatic and hydraulic actuations. What kind of disadvantage and challenges do you encounter during the process of designing the robot?
So one of the specifications that divide this problem is the size of the robot, because the motors, they don't scale well with the size of the robot. That's why it's hard to see a tractor excavator using electric motors. No, you use hydraulic, because if you need a lot of force and speed, it's really hard to use motors. So hydraulics is more efficient when you have heavy machines. Now, if you go to smaller machines, first it's hard to scale hydraulics down. Then it's the opposite. Scale hydraulics down is hard. You have the valves that has a size you cannot go less than that. And then you have the hoses, you have everything becomes more complex if you are in a small machine. So this is the first thing. So why this robot doesn't use hydraulics, why this robot doesn't use electric, depends on also the size of the robot. If the robot is big, it's hard to use electric actuators. Now, electric actuators are easy to deal with. They in general, they work fine, even if you do current control. You might have problems with friction in the gear ratio, the gearbox, and one of the challenges with electric-based legacy system is the gearbox, because a legacy system has a lot of impacts, and impacts they use to break the gearboxes. So that's why hydraulics is good, because for legacy system, because it can cope easily with impacts. You can have a lot of impact, and the hydraulics is robust to that. If you go to electric, you need to be careful with the amount of gear that you use, because if you use too much gear ratio, you lose the sensitivity in the other side. It's harder to estimate the things, and you might break it. And then if you go to a lower gear ratio, then normally you don't have enough torque. So it's really hard to design, depending on the size of the robot, to achieve, to have the good electric actuator. Now, the disadvantage of hydraulics is that it's more complex and it's more expensive.
Excellent. Moving to the next question is about, well, what is the starting point on the design process of quadruped robots?
Everything starts from, as a manipulator, everything starts from the task. You need to specify what the robot needs to do. This is the first point. Is a robot for outdoor, or it's a robot for indoor? Is a robot for indoor in an industrial environment, or is a robot indoor for a house, for housekeeping? No. First, you need to start from that. From that, you're gonna size the robot. And then you're gonna give a size for the robot, and you're gonna try to bring the environment the robot needs to work on into simulation. You're gonna then run your controllers. You're gonna run your controllers and try to understand what are the efforts the robot needs to do, the mechanical requirements. And these mechanical requirements are basically torque and speed. And then this will generate an envelope. You have the amount of torque, the amount of something that you find in the data sheet of motors and also valves, and then you need to find the actuators that you do that. So then on top of that, you also need to understand what kind of perception the robot needs to have, where you're going to place the sensors on the robot. Do you need to have lateral sensors? You can only have sensors on the top. The robot needs to look forward with the camera, or need to look down. So the process goes more or less like that, and then you go through this interactive process, because you need to allocate all the components inside, and that might change the shape. Then you need more space, and then you need to increase the size of the robot. And you update the robot. You go to simulation. You check if all the efforts in terms of torque and speed are still inside the envelope. And then when you stabilize, that's it. You need to start testing the actuators and the robot.
Talking about simulation, the next question is about which software is used for simulation in your robot.
The past, yeah. Nowadays, there is more. There is more.
Sorry. We're listening.
So nowadays we're using Gazebo. Gazebo is a simulator that can be used with ROS, and this is the rigid body engine that we use. It's Gazebo. It's a nice environment that allows you to include sensors and have an idea. You can include the environments, and it's much faster than doing something in MATLAB, let's say.
Okay. On the same topic, Gazebo, do you integrate Gazebo with ROS, or do you implement your own plugins in Gazebo without the help of ROS?
No, I don't. I mean, what we do is what you find in the tutorial.
Okay.
If you go through the tutorial of Gazebo in the ROS webpage, you're going to see how to run a robot simulation. You need to have the URDF that has the robot description, all these components to run, and then we also use a ROS control to run the algorithms to manage the controller. So there's no special plugin so far. I mean, there will be plugins for things, for example, also visualization. So there might be plugins to measure the ground reaction forces as well. Things like this.
The next question is about computer vision. It says, the training of the convolutional neural network, what kind of consideration have to be kept in mind before or during this process?
Not sure if I got the question. Can you repeat?
Yeah, of course. What kind of considerations have you to kept in mind before or during the process of training the neural network?
Well, I don't know if I'm going to answer what he expects to, or he or she expects me to answer. One of the things that we're always concerned is about computational power, because we don't want to have another computer, if possible, on the robot. The amount it takes to be trained is also important, because we don't want to, every time we change something, need to wait a lot of time to train again. And when you decide for something that is machine learning based, we are super concerned about the accuracy. And something that we don't do much in our lab is trying to let the neural network to do everything. So what we try to do in the lab is to use models as much as possible. And for what is missing and cannot be modeled, we use machine learning.
Okay, on the same topic, well, about perception, what are the methods are you using for the purposes of mapping? And what is the motivation for the choosing a specific method?
For mapping, I'm not sure if I understand the question. Can you repeat again? Then you give more time to think.
Yes, of course. It says, what are the methods are you using for the purposes of mapping? And what is the motivation for the choosing method?
So what we have in the lab is we use a software called GridMap that was developed by ETH. This grid map is basically you get the information from the camera. You get the information from the camera that is basically taking a picture of the environment. No, the camera is taking a picture of the environment, can be also depth image, so that shows also how deep is every point in the image. And then with that, we have an estimation of the robot position in the world. And then you say, okay, this image has this position in the world, and then we send to this grid map. This grid map algorithm is then putting them all together. And then with that, we are building the map. Now, this is basically what most of the people do. I mean, there's nothing else much you can do. All you need is to get all the point clouds, attach a position to it in a certain reference frame, and send to the algorithm that you put them together. The one that we use to put them together is this grid map. And what our controller does is then when it needs to do something, it calls a certain location or certain position, and that returns what is the height. So the kind of map that we use so far is called height map. It's not a 3D map. It's it's a height map that is basically for every XY position you have in the environment, you're going to have an associated height for the environment. So height maps, they work fine as long as you don't need to work with confined spaces. If you don't need to go under the table, because to go over under the table of navigating inside confined environments, you need to have a 3D map. Then you need to start using octomaps. And there's a long time we don't use octomaps anymore, and we're just focusing on the map, on the height map. So this basically what we use is height maps, and we use a software called grid map to put them together and to build the data to insert inside to give to the grid map. We have the real sense and also the state estimator that are then sending the map with certain reference coordinate.
Thank you very much, Dr. Victor. I think that, well, at least in the chat, we do not have any other question. I don't know if our audience have any other questions. Please, you can ask.
I have one question, please.
Please, Joe.
Okay. Hi, Victor. Firstly, thank you very much for your time. It's a pleasure to see you again. Thanks for that. So my question is about the new actuator developed by MOOC. Did you compare maybe the improvement between the old actuator and the new system, the new kind hydraulic actuator?
Good point. We actually didn't do like a fair comparison between them. What we could, I mean, we did more extensive tests for the rotor actuators, but we know not by heart, but we know more or less the bandwidth of the high Q has in the joints, and now we know the bandwidth of this one. In the air, they are quite similar. On the ground, we are achieving something better. But wouldn't be a fair comparison because we have a different structure. I mean, it's a fair comparison in terms of, okay, this is my actuator, this is my new actuator, this is my old actuator, okay. But the old system didn't have the same capability. So, for example, the force loop in high Q is running at 1 kilohertz. We can run the force loop at 10 kilohertz in the MOOC actuator. We are sampling the data at 10 kilohertz. We have the control loop, the current loop running for the valve, we are running at 10 kilohertz. We are running the spool loop at 5 kilohertz. And we didn't have this in the old system. So we expect, we are naturally expecting to have a better performance of the new actuator just because we have more powerful control loops. Now, what we want to do is to compare what is the performance of the actuator using feedback linearization. This is something that we didn't do yet, and that would be a nice comparison because we do feedback linearization in high Q and we do PID loops in high Q real. And we are working to do the feedback linearization, just that we got the code updated a few months ago. We didn't have yet people to work on that.
Okay, thank you very much. The other question is about all of your high Q versions already are using this new kind of operator or not?
New kind of?
New kind of actuator, the MOOC version.
No, the MOOC actuator is only used for high Q, for high Q real, this one that pulled the airplane.
The last one.
Yes, just the last one.
But when you when you implement some algorithms for your HiQ, you need, well, in this case, you differentiate between the version of the HiQ, right? You don't use in the same algorithm, the same control algorithm to control all of your HiQ versions robots.
It's the same control algorithm at the high for the high level part. Okay. So the same control that is running in HiQ is running in HiQ Real, and recently we bought another robot from a company, and we are using this again the same controller. So at high level, you can use the same controller because we are decoupling the system. No, we are sending the desired torques, and then you're going to have what we call the hardware abstract layer, that is the hull, that is interfacing with the low level. So this hull layer is receiving what are desired torques, desired positions, and interfacing with the actuators. So it's reading from the torque, the position from the actuators, and converting to the message that is read by the high level. So we have this layer that is separating the system. So when I go to another robot, I change the hull. Above is the same for HiQ, for HiQ Real, for HiQ to Max, whatever robot. The only difference is that basically from the hull to the bottom.
Okay, and yeah, the last question. Which is the pressure that you are using in the last HiQ robot, in the HiQ Real, right?
Yes, HiQ Real we are using. So for HiQ we are used to use 160, 170 bars.
Okay.
For HiQ Real we go up to 200.
200. But in the case of the HiQ Real, your pump is inside of the robot, right?
Yes, is everything on board.
Okay.
We have two pumps. We have one pump for the back legs and one pump for the front legs.
And the weight of these pumps is about how much in kilograms?
The hydraulic power units, they weigh about 11 kilograms, 10, 11 kilograms.
Wow. Great. So that's all my questions. Thank you, Victor. Thank you very much.
You're very welcome.
Thank you, Job, for the questions. We have one more question for the chat. It says, are you using the depth sensors of the RealSense camera?
Yes, we are using. That's what you're using to generate the maps used by CNN, for example.
Excellent. Is there any other question, please? You can put them to the chat or just talk directly with Dr. Victor. If there is no question, so I just have to say thank you very much, Victor, for your time and the excellent lecture.
Thanks. You're very welcome.
Thank you, Victor.
Okay.
Thank you very much.
Then thank you and bye and have a nice day.
Bye.
Have a nice day, Victor.
Muchas gracias a todos los participantes. Esta fue la última charla del día de hoy. Tenemos programadas 2 charlas más de mañana y una serie de charlas para la próxima semana a partir del día lunes. Así que los esperamos y nuevamente gracias por su participación el día de hoy.
Adicionalmente, tal vez agradecer, Jesús, indicar a los participantes que se les enviará el cronograma completo de las actividades para que lo tengan presente. A todos los registrados en el formulario de Google se les va a enviar el calendario para que así tengan en cuenta qué tipo de charlas técnicas se van a tener. Y bueno, gracias por su asistencia.
Claro que sí. Estén atentos a sus correos. En el transcurso del día de hoy les vamos a estar mandando el cronograma y los esperamos. Muchas gracias nuevamente por su asistencia.